Hello, my name is Brandon Sackstein, and I'm going to be talking about the experimental investigation of the static and dynamic behavior of a cantilevered beam. So this is the outline that I'm going to be going through today. So the laboratory objectives for this experiment are to use the strain gauge to measure the dynamic tip displacement of a cantilevered beam, compare the theoretical tip displacement of the beam to the measured values from the strain gauge, and create a spectrum analysis to determine and verify the natural frequencies of the beam. So this is the experimental setup. We had a quarter Wheatstone bridge attached to a beam here, and the strain gauge is on the beam, as you can see in the image. And then we had four different test scenarios. One of them where I manually displaced the beam with my finger. The second is I dropped a coin on the end of the beam to simulate an impulse. And then the third and the fourth, we're placing two different kinds of material, in this case, Scotch tape and carpet tape, on the bottom side of the beam. So here's a static measurement. So the sensitivity of the beam was calculated by plotting these values here, the deflection and the voltage, to get my sensitivity. And the sensitivity is used to convert from voltage to displacement. And this was gathered in lab 2, where we analyzed the average strain gauge voltages and the beam tip displacement by putting loads on this beam. So the static measurement, so in the static measurement, we also evaluated the stiffness of the beam, which allows us to convert from the load at the end of the beam to displacement as well, as shown here. So now in this experiment, as you can see, the blue section in the bottom figure represents the displacement on the beam, and then we removed that displacement to give you the top image. And in this top image, we isolated the peaks of the beam, or the peaks of the oscillation. And then using those oscillations, we're able to determine certain properties of the beam using those peaks. And then you can see over time, the beam oscillates towards zero displacement, showing that it's underdamped. And then here we used these following calculations to figure out what the natural frequency, the damping frequency, the damping natural frequency, and the damping ratio were, using these equations here. And this is called the decremental method. So here we plotted the experimental data versus the theoretical data. So the equation in that box down there is the theoretical equation there, and then the orange line on the graph represents the theoretical graph of that equation, and then the pink shows the actual experimental data gathered. And as you can see, it's a pretty good prediction for it. It's not too far off, but it's not perfect. And then here we have the spectrum analysis, and here you can see that the value gathered, the dominant one, the first frequency gathered is very close to the one that we gathered previously, and then you can see the second one is about 92 hertz. So here, this is the impulse example. So in the impulse example, again, we got rid of that first section there, and it's a little bit below zero because of the weight of the cantilever beam itself. And then from this example, we did another spectrum analysis, and we're able to see that the values are very similar to the previous example, which makes sense because the beam was not altered, so these values shouldn't have changed. Here, these are the different tapes that were used and applied to the bottom of the beam near the cantilevered, or the fixed end. And here's the results of all those tests. As you can see, as more material is added, the damping ratio goes up. And then here's all the examples here, all the data from each case. And as you can see, as more material is added, the damping ratio goes up. Case 1 and case 2 are vaguely similar. Case 3 was a little interesting. Not much material was added, so the natural frequency didn't change much, and the natural frequency didn't change much, which was interesting, even though material was added, but it must have not been significant. So in conclusion, applying initial displacement and impulse to the same Unaltered cantilevered beam results in the same damping ratio, damped to natural frequency and natural frequency. Adding small changes to the beam may not create significant change. Adding significantly more material to the beam increases all these values, and using fast Fourier transform is a way to predict several natural frequencies of the beam. And these are the references. Thank you.